Good problem solving starts with getting the problem statement right. Framing a problem well tells you what matters, what can be ignored, and what kind of solution is even worth trying. Edge AI only works well when the problem, the data, the hardware, and the people affected are all considered together. That makes responsibility part of the workflow itself, not an afterthought. A project becomes much more realistic when it starts with discovery and testing instead of assuming the first idea will work. Early experiments expose limits in sensors, latency, power, and field conditions before those limits turn into expensive failures. These two phases do different kinds of work. One narrows the problem until it is specific enough to judge, and the other checks whether that problem can survive real constraints. During discovery, the goal is to pin down what success means, who is affected, and what failure would look like. That gives the team a clear target before any model choice is made. Testing turns the idea into evidence. Each round shows what needs better data, what needs a different model, and whether the hardware can actually support the plan. In edge work, every design choice pushes back on the others. A data problem can change the algorithm, and a hardware limit can force the application itself to be redesigned. These parts are linked, not separate. Model errors reveal missing examples. Data availability limits algorithm choice, and device limits reshape what the system can do in the first place. A stream monitoring system can look straightforward on paper and still fail once the field conditions get real. Rare storms, noisy wildlife signals, and cold weather power limits can all point to a different sensing strategy or a narrower goal. The point of the loop is learning, not defending the first design. Real data should change what you collect next. Hardware tests should change how inference is structured, and field results should change the assumptions behind the product. Responsibility has to sit inside everyday design decisions, because those decisions determine who is helped, who carries the risk, and how visible the system's behavior really is. Waiting until deployment makes the hardest problems the most expensive ones. By then, the system may already be shaping outcomes, and the team has less room to change course safely. A mistake discovered too late can mislead customers, expose workers to risk, or force a costly redesign. The closer the system acts to the physical world, the harder those failures are to contain. A model that handles clean lab footage may react badly to shadows, lighting shifts, or normal staff movement once it is deployed. Responsible design asks in advance which errors are acceptable and who has to review them before the system affects work. Before any architecture decision, the team has to justify why edge processing belongs here at all. Sometimes cloud or even a simple rule system is cheaper, easier to govern, and easier to maintain. A strong design starts by comparing edge AI with simpler options. If cloud processing, a rule-based approach, or a lighter workflow solves the problem better, then edge AI is not the right default. Edge AI can bring speed, privacy, resilience, and lower bandwidth use. But those gains come with extra maintenance and operational pressure. The real test is whether the advantage is large enough to justify all of that overhead. A trail camera can benefit from local processing because bandwidth is limited and constant upload is wasteful. A stable temperature alarm often does not need a model at all if a threshold rule already does the job transparently. Once the problem is framed this way, the later decisions become more structured. Feasibility, model choice, and planning all start from evidence instead of enthusiasm. That framing turns vague judgment into a real review of ethics, business value, data, and technical limits. It also gives the team clear checkpoints for when to stop, revise, or move ahead. Employers look for people who can tell when AI adds real value and when it does not. That means asking for evidence before committing resources, not forcing AI into every opportunity. Edge AI only works well when technical choices and risk choices move together. The focus here is the workflow behind that, and why responsible design has to stay active from the first idea to the final deployment. Edge projects rarely move in a straight line. A problem shapes the data shapes the model shapes the hardware, and the hardware changes what data you can even gather in the field. That dependence is why the workflow is a loop, not a checklist. The first step is to understand the problem well enough to decide whether edge deployment makes sense at all. Only after that does prototyping become useful, because the early tests are there to reveal what the real environment is telling you. Discovery is about framing, not proof. You look for constraints like poor connectivity, tight latency, privacy pressure, power limits, or cost pressure, and those are the signs that local inference may be worth the extra effort. Once the problem is clear, the goal becomes evidence. A weak result can point to coarse labels, missing edge cases in the training set, or a device setup that hides useful signals, and each of those findings should change the next version of the system. That pattern shows up in monitoring systems all the time. If the readings are noisy, the fix may be physical or procedural rather than purely algorithmic, because placement, sampling rate, and annotation rules all affect what the model can learn. The important idea is that feedback has to flow both ways. Field performance should influence the model, but it should also influence the data pipeline, the device setup, and even the definition of the task itself. When a system struggles in the field, the response should be broad enough to reach every part of the pipeline. Sometimes the right fix is more representative data, and sometimes it is a smaller or better defined task that matches the environment more honestly. That is what continuous improvement means in practice. The system gets better when each round of testing helps it match reality more closely, even if the answer is to simplify the goal or adjust the hardware. Responsible AI belongs inside the same loop as the engineering work. Risk changes as the project changes, so ethical review has to stay active while the system is still flexible. A system that looks acceptable in a lab can become risky in the field when a user group changes, the deployment context changes, or the alerts feed into a more consequential decision process. Ethical review has to be part of the build, not a form at the end. The right questions come early. If errors could produce unsafe behavior, unfair treatment, surveillance creep, or exclusion, the project needs revision before those risks get baked into the system. A late surprise can spread through the whole system. A blind spot in the camera view, poor night visibility, or a missing human review step can force costly rework and can also create unsafe or unfair outcomes that were easy to miss earlier. Before model selection comes a more basic question: whether edge processing is justified for this problem. That choice depends on whether local inference really improves privacy, responsiveness, reliability, or cost enough to earn its complexity. The strongest design starts with the problem, not the technology. If a threshold rule or a cloud service already solves the task with less risk, then edge deployment is probably adding complexity without enough value. That trade-off matters because edge systems demand more from the team. The most advanced option is not automatically the right one. The right one is the one whose benefits justify the operational burden. That is why systems thinking matters so much here. The work sits where engineering, operations, ethics, and product judgment meet, so a good practitioner can keep all four in view while the project is still changing. The practical rule is to let feedback reshape the data, the model, and the hardware, while risk review stays active from start. Edge AI earns its place only when the problem, the deployment, and the safeguards all make sense together. A strong problem description comes before any model choice, hardware choice, or deployment plan. The goal here is to separate the real operational problem from the solution you might be tempted to build. That discipline matters in Edge AI because a vague idea can sound convincing while still being unusable. A good description stays focused on the situation, the failure, and the limits, not on a favorite fix. A problem description is a snapshot that tells you whether deeper analysis is worth doing. It gives enough shape to the idea that you can judge it without jumping straight into design. At this stage, you're not proving the system will work. You are collecting just enough structure to decide whether the opportunity deserves more time and technical effort. Start by naming the setting and the job being done. That gives everyone the same picture of where the problem lives and what operation is at stake. Then identify what people already do today, even if it is slow or imperfect. The baseline matters because every proposed system has to beat something real. Finish with the forces that make the decision hard. Power, connectivity, latency, budget, and maintenance all change what counts as a viable solution. When the problem cannot be stated cleanly, the project is not ready for a fit check. That usually means the idea still needs exploration before any technical judgment is useful. Later decisions depend on this anchor. If the statement keeps shifting, then business value, data needs, and technical options all drift too, and the discussion loses its shape. A clear description usually falls into three parts, and those parts keep the discussion grounded. Once they are written down, the problem becomes much easier to compare against possible edge solutions. The structure is simple, but it keeps the thinking disciplined. Each part answers a different question about the work, the gap, and the limits. Begin with the context and the operational goal. That first sentence should make the setting concrete enough that another person can picture the work immediately. A useful summary answers who is involved, what they need to accomplish, and the conditions around them. Concrete details matter because they shape every later technical choice. After the setting, describe how the work is failing right now. The point is to name the observed breakdowns, not to jump into proposed remedies. Write the trouble the way it shows up in practice. Missed events, slow review, late reactions, and weak coverage are all symptoms that help define the real gap. Now add the limits the solution has to respect. These are not side details. They're part of the definition of what can actually work. A solution has to fit power, connectivity, storage, latency, staffing, privacy, weather, and budget realities. Those limits tell you whether the idea is practical or only attractive on paper. Every project already has a baseline, even when nobody has named it yet. Finding that baseline is how you judge whether a new system improves the situation in a meaningful way. The baseline might be manual review, a rule, a cloud dashboard, a fixed inspection routine, or just doing nothing. Without that reference point, it is impossible to tell whether the new approach is better or merely more complex. A field example makes the structure easier to see. The same pattern appears in many edge AI problems: a real job, a slow workflow, and constraints that push the solution toward the edge. Picture cameras in a remote corridor where staff must pull memory cards by hand and sort through many near-duplicate frames. Most images are unhelpful, and by the time a rare sighting is found, the useful moment may already be gone. That field situation can be reduced into a format that is easy to evaluate. Once it is structured, the conversation can focus on facts instead of scattered impressions. The setting is a protected area, and the goal is to observe wildlife activity. That immediately tells you where the system lies and why the data matters. Today, the team waits, retrieves the cards, and reviews the images after the fact. That delay is part of the problem because the information arrives too late to act on quickly. The pain points are clear: long review time, lots of noise, and missed events. Those symptoms tell you why a better process is needed in the first place. The environment also limits what can be deployed. Weak connectivity, scarce power, weather exposure, and few maintenance visits all narrow the feasible options. Notice how the description still avoids design decisions. That restraint keeps the team focused on the problem before drifting into premature architecture choices. A template helps the same discipline travel from one project to another. Once the structure is familiar, you can frame a new opportunity quickly and consistently. The point is not the wording itself. The point is to force the idea into a shape that makes the scenario, workflow, problems, and constraints visible at once. Fill in the setting, the actors, and the job to be done. That one line gives the project its basic frame. Then write what happens now, including any workaround or manual process. The current method is important because it becomes the reference point for improvement. List the concrete consequences that make the current approach unsatisfactory. Good pain points describe what is going wrong, not what you think the fix should be. In with the boundaries that define feasibility. If a proposed system cannot fit those boundaries, it does not belong in the shortlist. A concrete example shows how the template works in practice. The details can change, but the structure stays the same. The setting is a packing line, and the operational goal is quality control before shipping. That makes the detection task time sensitive and tied directly to production flow. The baseline is manual sampling, which can catch obvious mistakes but not every bad seal. It also depends on operator time, which creates a bottleneck. Those are the observed problems. Hidden defects slip through, labor is consumed, and response time suffers. That wording stays on the behavior rather than the fix. The constraints push the design toward the actual production environment. Noise, vibration, staffing, and budget all determine what can be deployed responsibly. Once the problem is written this way, you have enough to begin judging feasibility. You still do not have enough to lock in a final design, and that distinction matters. Problem framing is a working skill, not a writing exercise. It is what lets technical and non-technical groups talk about the same operational need without talking past one another. That shared starting point reduces confusion across operations, management, domain experts, and deployment engineers. It also protects you from becoming attached to technology before the problem has earned a technical solution. The final habit is simple. Write the problem first and keep it short enough to stay useful. The rest of the process depends on that clarity. Use those four pieces as the input to later feasibility checks and deployment decisions. If the statement survives that scrutiny, the project has a solid base. If not, it needs revision before any design work can be trusted. A clear problem statement comes before any model, device, or deployment choice. The point is to define what is happening, what is failing, and what limits the possible solutions. Good project framing starts with plain language. If other people cannot judge the problem yet, the team is still too early in the process to lock in design decisions. The problem statement has a simple structure. Describe the setting, explain what is going wrong, and name the constraints that matter. That keeps the conversation focused on the real issue instead of on a favorite solution. Three parts are enough to make the situation legible. That structure is small on purpose because the first job is clarity, not completeness. Start with the setting and current workflow, then state the failures or harms, and finish with the realities any solution must respect. Those three pieces give everyone the same starting point. That is enough to show whether there is a real opportunity without pretending the answer is already known. From there, the team can ask whether the idea is worth pursuing, whether machine learning fits, and whether edge deployment is even sensible. Short, factual wording keeps the problem open for evaluation. It stops the team from smuggling in design choices too early and helps weak ideas get tested instead of protected. Once a description starts talking about models, architecture, or deployment strategy, the framing has already narrowed too far. That can hide better options and make one approach look inevitable when it is not. A concrete statement gives different people something they can agree on and later verify. A vague ambition may sound good, but it is hard to test and easy for everyone to interpret differently. A template helps keep the wording disciplined. It gives you a place for the setting, the failures, and the constraints without letting the description drift into a proposed fix. Use a fixed structure when the problem is still being shaped. That makes it easier to compare one opportunity against another and see where the real gaps are. The first line anchors the context. It tells people where the work happens and what the current process is trying to accomplish. The second line names the pain points in concrete terms. These should be failures, delays, costs, or harms that someone can point to in the real workflow. The last line keeps the team honest about the environment. Power, budget, staffing, connectivity, and safety limits all shape what counts as a workable solution. When this is done well, it is not paperwork for its own sake. It is a filter that tells you whether the problem is understood well enough to justify spending time and money on it. A trail camera project makes the structure easy to see because the setting, the failures, and the constraints are all very concrete. That gives us a clean example of how to frame a real operational problem. Field cameras gather lots of images, yet much of that material is low value or reviewed too late. The real cost shows up in storage, travel, and delayed decisions rather than in the camera itself. A strong version should be compact and specific. Each line should tell the reader something they can verify in the field. The scenario names the setting and the purpose in one line. It tells us where the work happens and why the cameras are there. The problems show up as wasted storage, slow feedback, and frequent trips into the field. Those are practical costs, and they're the reason the project might need a better workflow. The constraints are what keep the solution realistic. Any improvement has to work where the cameras are deployed, and it has to fit the resources the team actually has. That kind of statement does not argue for a specific technology yet. It gives the team a shared picture of what is broken, what is costly, and what the environment allows before anyone chooses device, cloud, or rule-based options. A problem description is the input to later decisions. It exists so the team can test feasibility, compare options, and make sure the eventual plan matches the real situation. That description supports questions about risk, value, data quality, and technical fit. It also helps decide between edge and cloud when the constraints point toward low latency, intermittent connectivity, or local autonomy. Employers value people who can turn observations into a decision-ready statement. That skill helps different parts of an organization work from the same problem instead of talking past one another. This is not just writing ability, it is coordination. Clear framing reduces misalignment, saves time, and keeps teams from building the wrong solution for a real need. The discipline is to keep the statement honest and unfinished at the right level. It should tell the truth about the problem without quietly turning into a proposal. If the wording is too broad, narrow it. If it starts naming a technology, strip that out. If it contains a fix, save that for later review. The best wording stays focused on the situation itself. The goal is a short statement that makes the broken part, the constraints, and a reason for further evaluation visible. Once that exists, the next questions become practical: feasibility, edge deployment, and the shape of a plan worth building. The central question is whether local deployment actually changes the problem enough to matter. That decision should come from the system's needs, not from a default assumption that edge is always the right place. A useful way to think about deployment is to treat it like any other architecture choice. The question is not whether edge sounds modern. The question is whether putting intelligence near the data creates real value for this specific job. Blurb helps by prompting that kind of evaluation without turning it into a rigid scorecard. The first move is to judge the benefits before thinking about hardware. If the edge improves one important dimension enough that can justify a closer look even when the rest of the profile is ordinary. A local model might respond faster, avoid expensive data transfer, or keep sensitive information from leaving the device. Those gains do not all have to appear at once. One strong benefit can outweigh a weaker showing elsewhere if it changes the system in a meaningful way. That benefit-first mindset prevents a common mistake, forcing edge deployment onto a problem that does not need it. If the network is already reliable, a central server is already available, or cloud processing is cheap and simple, local deployment may only add complexity. In that case, the cleaner answer may be cloud only. A remote sensing site is a good place to see why locality matters. When bandwidth is limited and connectivity comes and goes, the system needs to make decisions where the data is being produced, not after a slow round trip to a distant server. Picture a field site sending a steady stream of sensor or camera data. If everything has to travel back to a central system, the delay and transmission cost can become a real burden, and sometimes the data cannot even get through when it matters most. A local model can filter, classify, or flag events on site, so the system keeps reacting immediately. That is exactly the kind of case Blurb is meant to reveal. The value may come from responsiveness, from practicality, or from both, and you do not need every possible benefit before local execution becomes worth considering. A model can be valuable and still belong in the cloud. The real question is whether moving it onto the device improves the overall system enough to pay for the extra deployment effort. Hospital imaging makes that distinction clear. The AI task may help triage scans or highlight suspicious regions. But if the hospital already has reliable infrastructure and centralized workflows, the edge may not add much. The issue is deployment value, not model value. Often the cloud or institutional compute setup is simpler to manage and easier to update. If the model needs heavy compute, frequent retraining, or direct access to centralized records, putting it on device can create more burden than benefit. When the surrounding system is already strong, edge can become a solution in search of a problem. That judgment should happen early, before architecture gets locked in. When the cloud already meets the needs for latency, compute, and reliability, edge deployment may add maintenance without adding enough value. Some workloads fit centralized resources better. They may be compute-heavy, need large memory, or be easier to secure and govern in one place than across many devices. In those cases, cloud infrastructure can be the simpler and smarter choice. Edge deployment matters when locality creates the value. The system must keep working without a connection, respond with very low delay, or keep data near where it is generated. If those needs are not present, a centralized design is often simpler, cheaper, and safer. Many systems land between the two extremes. A hybrid design lets the local device handle immediate work, while the cloud handles the heavier tasks that do not need to happen on site. That split is often the best balance when only part of the workload needs to stay local. The edge can do the fast first pass, and the cloud can take over for analysis that benefits from more compute or more context. A smart speaker is the classic example. The device can detect the wake word locally, then send the audio onward for transcription and deeper language processing. The same pattern works for field cameras and warehouse systems. Local detection first, remote review only when it matters. Blurb works best as a screening tool. It helps you ask the right questions about whether edge deployment earns its place in the design. The point is not to produce a perfect score. The point is to quickly test whether the edge creates enough concrete value to deserve deeper investigation. Ask whether the system becomes noticeably faster when the model runs close to the data. If latency matters, that alone can be a strong reason to keep evaluating the edge. Look at whether local processing reduces how much data needs to move. When the raw stream is large or expensive to send, filtering at the source can save real cost. Some data should stay near where it is created. If keeping information on device lowers exposure or simplifies compliance, the edge may be doing real architectural work. If the system must continue working during network outages or weak signal, local execution becomes much more attractive. Resilience can be more important than raw performance in field settings. Sometimes the question is simply whether the system can be used where it lives. If local processing makes deployment, operation, or inspection easier, that practical advantage may be enough to matter. No one is trying to compute a perfect total. A few clear wins can keep the edge idea alive, while mostly negative result points back toward the cloud. Mixed results often suggest a split design instead of an all-or-nothing choice. That kind of judgment matters well beyond a single project. Good planners avoid over-engineering, resist hype, and match the solution to the real constraints, which saves money and reduces churn. The decision comes down to whether locality changes the system in a meaningful way. If it does, keep exploring the edge. If it does not, do not force it into the design. And if both sides have a role, let the workflow decide how the work should be divided. By the end of the judgment, the answer should land in one of three places: genuinely better on the edge, better in the cloud, or best as a hybrid system. What matters is having reasons that tie back to the problem, not the platform. The question is whether edge deployment earns its place in the system. The decision starts with the problem itself, not with the technology stack. Blurb is a quick way to test fit before design decisions get complicated. It gives you 5 practical lenses for asking whether local processing creates real value or just extra work. That phrase matters because this is not a scoring system. It is a first pass for finding whether any of the edge advantages are strong enough to justify deeper work. Each term points to a different reason to move computation closer to the device. Bandwidth, latency, cost, reliability, and privacy are separate pressures, and any one of them can be enough to matter. The point is to look for a compelling constraint, not a perfect checklist. Real projects often move toward the edge because one problem is painful enough to outweigh the extra complexity. Remote sensing is a classic place where edge processing makes sense. The environment itself creates the conditions that favor local decisions. A trail camera may sit far from reliable connectivity, so moving every image would waste bandwidth and power. Local detection lets the device keep the useful event and skip the raw flood of data, which helps cost, reliability, and sometimes privacy too. That is why edge thinking feels natural here. Distance, intermittent network access, and large data volume all point in the same direction. So Blurb gives a clear practical argument for local processing. Some problems look edge-friendly at first, but the full setting changes the answer. The real question is whether the main constraint is already handled elsewhere. Medical imaging can seem like an obvious edge case because the data is sensitive. But if the facility is already connected, centralized review is normal, and latency is not the bottleneck, then a cloud or centralized workflow may already meet the need. That is the useful counterexample. When a network setup already solves the key problem, edge deployment may only introduce more moving parts, more maintenance, and more cost. The mistake to avoid is treating edge as the superior option by default. It can be the right choice, but only when the trade-offs line up. Those costs add up quickly. Distributed devices increase software complexity, need broader team skills, and often force smaller models. They are harder to update, easier to break in the field, and more exposed to tampering. That is why the decision has to be earned. In some systems, the edge pays for itself, and in others, it just spreads effort across more places. Sometimes the answer is mixed rather than absolute. A split architecture lets different parts of the workflow live where they make the most sense. A hybrid design works when immediacy and heavy computation belong in different places. The edge can handle fast local decisions, while the cloud can handle broader processing and coordination. Smart speakers fit that pattern well. A wake word detector runs locally, then the harder language tasks move upstream. Industrial inspection can use the same split, with local filtering on the floor and deeper analysis or record keeping in the center. That framing removes the false choice between edge and cloud. The better design is the one that places each step of the workflow where it performs best. This judgment is not only technical. It is a planning skill that helps you justify architecture decisions to people who care about cost, reliability, privacy, and delivery risk. That skill matters because organizations need people who can choose the right deployment model, not just build a model. Clear blurb reasoning helps you defend the choice and avoid adding complexity for no gain. Start with the workflow and the constraint, then see whether edge deployment changes the answer in a meaningful way. If it does, keep going. If not, stay with the simpler architecture. If the answer is mixed, split the work. That decision tree should sit beside the pros so the path is visible as well as logical. The visual branch point should match the reasoning. First the problem, then the deployment choice. The goal is to answer that question with specific blurb reasons, not with habit or fashion. If edge helps, say why. If cloud is enough, say that too. If both are needed, name the split clearly. The real question is whether a model earns its place at all. The goal here is to decide when rules are enough and when learning actually solves a problem that simpler logic cannot. Training a model is only worth doing after the problem proves too hard for a direct solution. If a deterministic approach can handle it cleanly, that is usually the better engineering choice. A rule-based design is often easier to inspect, cheaper to run, and simpler to test. When a task can be expressed with conditions, thresholds, counters, or state transitions, that option deserves serious consideration instead of being treated as a backup plan. The first source of structure is domain knowledge. If people already understand the process well, that understanding can often be turned into explicit rules or into pre-processing that makes the final decision much easier. A raw sensor stream does not always need learning. Sometimes filtering, smoothing, feature extraction, or event detection gives you a clean enough signal for a rule to act on, and that keeps the system transparent. That works especially well when the process is stable and the signals are bounded. Alarms, trip points, and basic checks are often better handled by fixed logic because the behavior is easy to interpret and verify. A useful test is whether the messy input can be simplified first. If pre-processing turns the problem into something the system can decide with clear logic, that is usually a strong sign to stay with rules. The same question becomes clearer in a concrete system. Riverwatch node can often be solved with thresholds and time windows, but changing conditions can push it toward a learning problem. If the task is spotting obvious events like sustained turbidity, a sudden temperature shift, or repeated motion near the bank, simple rules may be enough. When the sensors are steady and the patterns are consistent, deterministic logic can do the job well. A more variable watershed changes the picture. Rain, seasons, upstream activity, sensor drift, and animal movement can overlap in ways that make the boundary between normal and abnormal much harder to write down by hand. That is the point where machine learning starts to make sense. The attraction is not fashion. It is that the pattern space has become too irregular for tidy rules to capture reliably. The issue is practical, not philosophical. Rules stop being attractive when they require constant tuning, exception handling, and manual maintenance just to keep up with the data. A rule set can still be written even when it no longer feels clean. The problem is that the work of keeping it correct starts to grow fast, and the logic becomes harder to manage over time. Every new exception adds another branch to the logic, and the special cases start to pile up. At that point, the rule system is spending more effort surviving edge cases than capturing the normal pattern. When conditions interact, the behavior is no longer obvious from reading the rules one by one. Small changes in one condition can affect another, and the whole system becomes difficult to predict. Variation across locations, or time periods, is a warning sign too. A logic tree that works in one environment may need major rewriting when the context changes. When new cases keep breaking the same, supposedly simple rules, the design has stopped being simple. You can still patch it, but the patches tend to accumulate into something fragile. Rules may still be possible in principle, but that is not the real test. If they're too expensive to maintain in practice, the handcrafted approach has become fragile. Machine learning becomes attractive when the data is noisy, high-dimensional, or hard to describe with a small set of explicit rules. The edge often faces exactly the kind of messy input. Images, audio, accelerometer traces, and multi-channel telemetry can contain patterns that are real but subtle. A small rule set may miss them, while a model can sometimes learn those patterns from enough examples. Freshline Inspector is a good contrast. If inspection depends on images or image-like feeds, changes in lighting, orientation, texture, and defect size can make fixed rules awkward, while a model may learn the distinctions more naturally. That condition matters because the data has to support the model. Machine learning is useful in the right setting, but it never replaces the need to check whether the problem actually fits it. The decision also depends on the project costs. In edge systems, the hard parts are usually data, labels, and whether the training data really matches the deployment environment. The drawbacks are mostly operational. You have to collect data, label it, and keep trusting that the training setup still represents the real world after deployment. A model needs examples that reflect the behavior you care about. Rare events, changing conditions, and hard-to-capture cases can make training much less reliable. Even if the data exists, someone has to decide the correct target for each example. When that judgment depends on experts, labeling becomes slow, expensive, and sometimes inconsistent. A model also learns the environment it was trained in. If the field setup differs from the lab setup, performance can drift in ways that are not obvious until the system is already running. That risk is especially sharp at the edge because one site, one season, or one device configuration may not generalize to another. A dataset can look adequate and still miss the real operating conditions. Once the stakes rise, the question is no longer only accuracy. People also need to understand the decision and trust that the model's bias is acceptable for the setting. For low-stakes outputs, some uncertainty may be acceptable. But when a result affects safety, operations, or accountability, the ability to explain the decision becomes part of whether the system is even usable. No dataset can cover the whole world, so some bias always exists. The real issue is whether the bias stays within tolerable limits for the conditions the system will actually face. In consequential settings, usually works may not be enough. If the system has to be auditable, deeply constrained, or provably reliable, a probabilistic model may be the wrong tool for the job. A practical example makes the risk easier to feel. A model can look strong in development and still create serious trouble once it meets a different real-world environment. Imagine an industrial safety alarm trained on machine sounds. In one factory, it performs well, but in another, the acoustics, where patterns and background noise are different enough that the alarm starts behaving badly. Then the problem spreads beyond accuracy. Operators begin to ignore warnings, trust erodes, and the false alarms can hide the very incidents the system was supposed to catch. Even when a model is useful, replacing the person is not always the best design. In ambiguous or high-consequence tasks, the model often works better as support for a human decision-maker. The model can filter, rank, highlight, or summarize, while a person makes the final call. That keeps human judgment in the loop when the task has uncertainty or serious consequences. Riverwatch node might flag the most suspicious intervals instead of declaring an event on its own, and Freshline Inspector might prioritize likely defects for a technician. In both cases, the model assists the workflow without pretending to be the final authority. That approach gives you assistance while staying honest about uncertainty. It is often the safer bridge between a noisy problem and a human decision. A short checklist keeps the choice grounded. The point is to compare rules, data, complexity, and risk before committing to machine learning. The decision becomes easier when you force it into a few concrete questions. That way, the choice is based on the problem shape instead of on habit. Start with rules and pre-processing, then test whether the input is too complex for hand-built logic. After that, check the quality of the data and labels, and finally ask whether the stakes tolerate the explainability and bias trade-offs. If the first answer is yes, begin with the simpler design. If machine learning still looks justified, treat it as one candidate among several. And if uncertainty remains high, consider augmentation before full automation. That discipline is what strong engineers are judged on. The best choice is not always the most sophisticated one. Often it is the one that is simpler, safer, and easier to defend. The decision point here is whether machine learning adds real value or just extra complexity. The focus stays on visual and sensor-rich problems, where the input can be messy enough that simple rules stop working well. The useful question is whether machine learning belongs in the problem at all. That matters because many edge tasks are handled better by rules, thresholds, or a small set of heuristics than by a learned model. That shift changes the whole design conversation. Once the task can be solved clearly with deterministic logic, the model adds cost, uncertainty, and maintenance work without giving much back. When a job is a straightforward boundary check or a known pattern in stable data, a hand-built rule is often the better first choice. Those rules are easier to inspect, debug, and trust, and they avoid the overhead of labels and training. Machine learning becomes more attractive when the input space is too rich for explicit rules to hold up. Images, audio, vibration signals, and other real-world sensor streams often create exactly that kind of complexity. The first pass should always favor the simplest workable approach. If a rule solves the problem cleanly, there is no reason to jump to a probabilistic model. That design habit keeps projects grounded. It pushes you to prove that the simpler option fails before you pay for more complexity. Reliable rules are valuable because they give you exact behavior with very little machinery. If they already solve the task, they usually beat a model on speed, cost, and clarity. Once the input changes too much for fixed logic to survive, the rulebook starts failing on edge cases. That is the point where learning from data begins to make sense. When a task is important but still ambiguous, a person in the loop can reduce risk without forcing full automation. That keeps judgment where it matters most while still gaining some of the efficiency of model. This is engineering discipline, not resistance to ML. On limited hardware, the simplest system often wins because it is cheaper to run, faster to deploy, and easier to maintain. Perception tasks are the big signal that rules may not be enough. Once the system has to interpret a rich scene, the link between input and outcome becomes too complicated to write down by hand. A trail camera sounds simple at first. Detect motion, save the frame, flag a large shape. Real scenes break those rules fast because wind, lighting, angle changes, and partial occlusion create cases that fixed logic cannot cover well. The same pattern shows up in visual quality checks. Once defects depend on surface texture, glare, contamination, or small deformations, a threshold-based rule set turns into a fragile patchwork of exceptions. That is why visual evidence is such a strong reason to consider ML. The data contains a lot of detail, but the decision boundary is often too messy to encode manually. Machine learning can model patterns that are hard to express as rules, but that capability comes with trade-offs. The useful question is whether the gains outweigh the extra demands. The advantage of ML is flexibility. The cost is that you now depend on data quality, model behavior, and ongoing maintenance instead of a fully explicit rule set. A model learns from examples, so the dataset has to match the real problem closely. If labeling is expensive or inconsistent, the model can end up learning noise instead of the signal you wanted. A deterministic rule can be traced line by line, but a learned classifier is harder to justify in plain language. That becomes a problem when someone asks why one item was accepted and another was rejected. Models also inherit the environment they were trained in. If the training data comes from one camera, one facility, or one operating range, the system may fail when the real world looks different. A model can look excellent in testing and then stumble in a warehouse aisle with glare, shadows, dust, and occlusion. That gap is not a bug in ML itself. It is a mismatch between training context and deployment context. Another filter is the kind of correctness the task demands. Some systems can tolerate approximation, while others need behavior that is exact and defensible. That distinction matters a lot in practice. If being close is good enough, machine learning can be a reasonable fit. If not, the bar rises sharply. Safety-critical and compliance-heavy work often needs traceable decisions. A probabilistic model may help, but it usually cannot provide the same proof-like guarantee as a deterministic rule. That is why support roles are more comfortable for ML than final authority roles. Ranking cases, surfacing candidates, or summarizing evidence is one thing. Making the final call in a high-stakes domain is much harder. When the pattern is useful but the risk is still real, a person can stay in the final decision path. That gives you a safer middle ground between full automation and doing everything manually. That split is often enough to make the system practical. The model does the first pass, and the human handles the judgment call. In visual inspection and monitoring, that setup works especially well. The model can reduce a huge stream of data to a manageable review queue, and the person can correct false alarms or catch misses. That is augmentation rather than full automation, and it is often the right compromise. If the system saves attention and time while leaving judgment in human hands, it is doing a useful job. This judgment matters beyond the architecture choice itself. Teams need people who can decide when ML is unnecessary, when it is justified, and when a human review step is the safer design. That ability helps teams avoid wasted prototypes and unnecessary complexity. It is as important as knowing how to train a model because it keeps the project aligned with the real problem. Good product and technical judgment has direct business value. It saves money, lowers deployment risk, and stops model enthusiasm from outrunning reality. A simple test can keep the decision honest. If the logic is easy to state, the data is manageable, and the risk is low, rules may be enough. Otherwise, ML may earn its place. That frame is usually defensible in real projects. It forces the choice to rest on data fit, explainability needs, and risk rather than on habit or excitement. That is the right skeptical question for edge work. The best solution is usually the one that solves the task cleanly with the least machinery, not the one that adds machine learning by default. The goal here is to practice problem framing before you reach for a solution. Strong edge AI work starts with a clear judgment about what the real problem is, not with guessing the architecture first. Treat this as a checkpoint for reasoning. If you can identify the actual need first, the technology choice becomes much easier to defend. Strip away the buzzwords and say what is happening, what outcome you want, and what decision has to be made. That keeps you from jumping too early to cameras, models, microcontrollers, or cloud services that may not belong in the design at all. The next move is to convert a messy scenario into a clean problem statement. Once the problem is clear, you can judge whether rules, machine learning, edge compute, or some mix of them actually make sense. Each example shows the same habit from a different angle. The details change, but the first task is always to isolate the decision that really matters. The important question is not how to build a drone system, but how to identify the parts of the field that need treatment. If the queue is simple, rules may be enough. If the patterns are messy, machine learning helps. If the decision must happen locally, edge compute becomes relevant. The real problem is occupancy detection with useful timing, not adding AI for its own sake. Depending on the sensors and conditions, a simple presence signal may work, or a learning-based detector may be needed for occlusion, lighting changes, and noisy inputs. The decision to support is early wear detection, not classification as a standalone exercise. Stable indicators can be handled with rules, but subtle and inconsistent patterns are a better fit for machine learning, especially if the system has to run in the vehicle, shop, or roadside device. These prompts matter because they train abstraction. A messy opportunity becomes usable once you can restate it in a way that exposes the technical tools that might actually help. After the problem statement comes a narrower question. What kind of solution is this really asking for? The answer may be edge compute, machine learning, both, or neither if a simpler sensor or workflow solves it better. That choice protects you from forcing a favorite tool into the job. A good design starts by asking what the situation demands, not by assuming every problem needs a model or a device at the edge. Engineering begins with the unconstrained version of what would be most useful. Then you test that idea against cost, latency, infrastructure, and implementation difficulty, instead of shrinking the problem around the technology you already know. That ideal version is a direction, not a guarantee. It helps separate desire from feasibility because the best-seeming answer still has to survive budgets, devices, data, risk, and operations. A warehouse security case makes the shift from vague idea to defensible design more concrete. It gives a target outcome first, then lets feasibility questions decide what kind of system is actually sensible. The ideal version names outcomes, not products. Detect suspicious movement, reduce false alarms, alert staff quickly, and keep footage local unless escalation is needed. That framing keeps the conversation on the mission instead of the gadget. Once the target is clear, the reality check starts. Feasibility breaks into 4 separate tests, and each one can stop a project from being a good idea. First, ask whether the system crosses ethical lines. A technically clean design can still be unacceptable if it creates unfair surveillance, overreach, or unnecessary privacy intrusion. The question is not only whether the system works, but whether it should exist in that form. Monitoring more than necessary or treating people as threats by default can make the whole project a poor choice. Next, ask whether the project solves a real operational pain point strongly enough to justify the cost and disruption. Clever systems fail when they do not deliver enough value to survive maintenance and organizational change. A useful system has to earn its place. If the business value is weak, the project may be interesting but still hard to sustain. Then, check the evidence. A strong detector is only as good as the data you can actually collect and maintain, including normal cases, rare incidents, and edge cases. If the team cannot build a representative dataset, the model will be fragile. Missing rare events or unusual conditions is often enough to weaken the whole plan. Finally, test the hardware and deployment reality. Even a good idea fails if the site cannot support the required latency, power, network access, or maintenance burden. A design has to run reliably in the environment where it lives. If it needs more compute, bandwidth, or upkeep than the site can handle, it is not feasible no matter how attractive it looks on paper. A project only works when moral fit, business fit, dataset fit, and technology fit all land in a reasonable range. If one of them is badly off, the idea needs revision, not enthusiasm. That warehouse example is useful because it turns a broad idea into a sequence of tests. Define the ideal outcome, then pressure test it until what remains is buildable, defensible, and worth the effort. The people who help most are often the ones who can restate a vague request clearly and choose the right abstraction. They know when a project should move forward, change shape, or stop entirely. Keep that habit steady. Restate the problem, identify the right technical abstraction, and only then decide whether the opportunity deserves more investment. If the path is still fuzzy, refine the problem. If no viable path remains, stop early. If it holds up, move ahead with a grounded plan. Practical judgment matters here. The same technology can be appropriate, unnecessary, or even harmful depending on the problem. The goal is to learn how to frame an application clearly and test whether Edge AI is actually the right fit. A strong project starts with the outcome you want, before any talk of devices or models. If the problem is stated well first, technology becomes a response to need instead of a premature guess. These examples are useful because they look different on the surface, but each one can be analyzed with the same method. The point is to practice turning a vague opportunity into a clear problem. That need sounds simple, but the real question is how to identify variation in the field well enough to act on it. Once that is clear, you can judge whether sensing, prediction, or a local control system belongs in the solution. Here the success condition is convenience with low disruption. The system has to detect presence reliably while respecting guests and avoiding a labor-heavy process. This one adds urgency because the value comes from early warning. The useful system is the one that spots where soon enough to prevent failure, downtime, or an incident. That shift in question changes the whole exercise. Instead of chasing a model first, you define the real job the system must do, and that makes the later design choices much clearer. A useful statement names the people involved, the setting, the frequency, the limits, and the cost of getting it wrong. The sharper that language becomes, the easier it is to decide whether edge compute, machine learning, both, or neither belong in the project. The ideal solution step is where you separate the goal from the limits of the current setup. That keeps the problem from shrinking to whatever tools happen to be nearby. That is not naive thinking. It is a way to avoid letting hardware, budget, or habit decide the problem before you do, and it helps reveal what success would really look like in the best case. Once the goal is clear, the technical choice becomes much more disciplined. Some problems need local processing, some need pattern learning, some need both, and some are better solved with a simpler workflow. A clever system can still be the wrong project if it is too costly, too risky, too private, or too hard to maintain. A good idea has to survive practical scrutiny, not just technical admiration. With the ideal solution in mind, the next step is a structured check. These four lenses keep the project grounded in reality before any architecture gets locked in. Each screen asks a different kind of question, and all of them matter. If one fails badly, the project needs revision before it becomes an expensive mistake. The moral check asks whether the system creates unacceptable harm or unfair treatment, or whether it crosses lines around consent and notice. Some ideas fail here, even if they are technically impressive. A project also has to earn its place economically. If the benefit does not justify the cost, risk, and ongoing operational burden, the idea may not be worth building. A model or detection system cannot learn from data that is missing, irrelevant, or badly matched to the real setting. The question is not just whether data exists, but whether it is the right data for the task. The final check is whether the deployment environment can actually support the solution. Latency, power, network access, upkeep, and reliability all have to fit the site where the system will live. These checks interact, so success in one area does not rescue failure in another. The purpose is to distinguish something that sounds possible from something that can really be built and run responsibly. A warehouse setting makes the method concrete because the goal, the risks, and the deployment constraints are easier to separate. The same framing process can then be reused in other applications. The useful outcome is not just detection. It is timely detection with alerts that people can trust. If the alarms are noisy, the system loses value very quickly. The technical choice depends on what the warehouse actually needs. Simple conditions can be handled with rules. Visual distinction may require learning. Local video processing may call for edge compute, and some setups need both inference and learn classification. Now the four lenses decide whether the idea survives. Security systems can raise privacy issues. They must justify their cost. They need real warehouse data, and they have to work with the actual cameras, networks, and alerting systems on site. That discipline keeps the project tied to an operational result instead of a technology preference. If a simpler solution works, use it. If Edge ML is justified, make the case. If the risks are too high, stop early. Employers notice when someone can turn a vague request into a scope problem and then judge the right deployment approach. That combination of framing, technical judgment, and constraint checking is useful across Edge AI, applied ML, and product-oriented engineering. The strongest candidates do more than build, they decide. They can separate on-device, cloud, rules, or hybrid solutions, and then explain why one path fits better than another. That is the practical habit to keep. Frame the problem first, then challenge it with moral, business, dataset, and technology questions. If it survives, the architecture choice is defensible. If it does not, the problem needs revision before any build starts. Moral feasibility asks whether a project should proceed at all, not just whether it can be built. The point is to catch ethical blockers before technical effort goes too far. A go/no-go decision means the project either clears the ethical bar or it does not. That framing matters because some ideas should be stopped before prototype work begins. Technical elegance does not make a project morally acceptable. If the system would cause unacceptable harm, break consent, or cannot be tested responsibly, then the right decision is to stop, even when the model looks promising. Moral feasibility works like any other feasibility check. It asks whether the idea can survive real-world constraints. The difference is that the constraint here is harm to people, groups, or institutions. A technical bug can usually be fixed with engineering work. Ethical failure can damage trust, trigger scrutiny, create resistance, and leave lasting harm that no patch can undo. The ethical review has to follow the whole life cycle, from data collection to long-term support. That broader view catches harms that never show up in the final model output alone. A project can create harm long before it reaches users, and it can keep creating harm after deployment. Building, testing, and support all deserve the same ethical attention as the product itself. A A useful review starts by naming the stages where risk can appear. Once those stages are visible, the specific harms become much easier to spot and discuss. Data collection raises the first consent question. Did people know they were being observed or measured? And did they have a real chance to object? Hidden collection is often the first ethical problem. Labeling can embed judgments about people before the system even runs. If those judgments are sensitive or poorly justified, the harm starts in the dataset, not just in the model. Testing is not ethically neutral if it can disturb normal operations or affect real people. A pilot that creates disruption is already producing consequences, not just evidence. Deployment often changes power relationships. Once the system is live, it can alter how people are monitored, evaluated, or treated in everyday work. Support matters because real systems drift, misfire, and become part of routine workflow. Ethical review has to include what happens after the first release, when problems are harder to notice but easier to normalize. Many harms are indirect rather than physical. A warehouse system may never injure anyone directly, yet can still create surveillance pressure, reputational damage, environmental trade-offs, or changes to jobs and responsibilities that matter a lot. The first ethical pass does not need certainty. It needs a disciplined way to surface concerns early so they stay visible while the project takes shape. Early review is about visibility, not final judgment. If a concern is already clear enough to name, it should be written down instead of pushed aside. A good concern list changes as the project becomes more concrete. That is why the list should be revisited, updated, and kept honest rather than treated as a one-time memo. Once the idea becomes concrete, the ethical questions become concrete too. A warehouse example makes the risks easier to name in practical terms. A system that flags the wrong person can create immediate unfair treatment. False suspicion is not a minor error when it affects how someone is seen or handled on the job. Constant surveillance changes behavior, even when nothing obvious goes wrong. People may feel pressure, stress, or reduced autonomy simply because they know they are being watched. Privacy becomes an issue as soon as recordings or sensor data include people who never agreed to participate. That concern is stronger when the capture is hard to avoid or hard to notice. Uneven performance across groups or conditions is a practical fairness problem. If lighting, uniform, body type, or job role changes the outcome, the system needs scrutiny before anyone relies on it. Too many false alarms can turn a safety tool into a distraction machine. When alerts pile up, attention gets consumed and the environment becomes harder to manage responsibly. A system can create secondary harm by moving burden onto guards, supervisors, or line workers. Even if the model performs well, the surrounding workflow may become harder, slower, or more stressful. The goal is not to predict every harm with certainty. The goal is to identify which concerns are serious enough to stop the project, force redesign, or require stronger safeguards before work continues. Some ethical questions belong at the very start because they can shape the whole project. Consent, privacy, fairness, and test safety are part of that early screening. When cameras, microphones, location traces, or other sensors are involved, consent and privacy need to be documented before the prototype grows. People who never intended to join an AI system can still be captured by it. Testing safety belongs on the early checklist too. A pilot that causes false alarms or disruption is already affecting real people, especially when the system runs in ordinary places like workplaces or public spaces. Fairness is practical, not abstract. If one group is more likely to be flagged, delayed, ignored, or burdened, that difference has to be investigated before deployment. A serious review needs more than one voice. Different people notice different risks, and a narrow review often misses the harms that matter most to the people affected. The best review teams combine local knowledge, ethical judgment, and lived experience. That mix helps reveal blind spots that the technical team may not see on its own. Broad participation is not just process overhead. It is a practical check on optimism bias, because the person proposing the system usually sees the intended benefit more clearly than the downstream harm. Ethical approval is not a one-time event. The real standard is ongoing review, because the conditions around a system keep changing after the first decision. Projects evolve as data changes, models drift, and workflows shift. A deployment that seemed acceptable in a pilot can become problematic once it is scaled or used in a different setting. The habit to build is simple. Keep the risk list active, revisit assumptions, and ask whether the system still deserves to exist in its current form. If harms grow, the design should change. If they cannot be reduced enough, the project should stop. Stopping or reshaping a project is not indecision. It is the kind of judgment that comes from taking responsibility for consequences, not just for code. For employers, this kind of analysis shows more than technical literacy. It shows that you can spot ethical blockers early, talk across teams, and avoid spending time on something that should not clear the first gate. If the project survives this review, the decision is not finished. It just means the team can continue with better guardrails, clearer documentation, and more explicit responsibility for the system's effects on the people around it. Moral feasibility asks whether an edge AI system can be pursued in a way that is ethically defensible, not just technically workable. The focus is on the real effects on people and the decisions that follow from them. A project does not earn a pass just because the technology can be built. Ethical review has to function like a gate, stopping work when the harms are too serious to justify. The first check is blunt. Even if the system works as intended, who might still be harmed or treated unfairly? If those harms cannot be justified or reduced, the project should not continue unchanged. A technical miss can often be repaired with tuning or retraining, but moral harm spreads much further. Privacy violations, discrimination, and public backlash can damage trust, reputation, and compliance in ways that are far harder to fix. The ethical review has to cover the entire project, from data collection through maintenance. A model may look harmless on paper and still become problematic once it reaches people and real workflows. The useful habit is to trace the system stage by stage, because harm can enter at several points. That wider view catches risks that would be missed if attention stayed only on model accuracy. product behavior matters because the real question is how people experience the system. A design can look neutral in a spec sheet and still feel intrusive, biased, or disruptive in use. Data collection deserves its own scrutiny because ethical problems often start before the model is trained. Notice, consent, and purpose limitation tell us whether the data was gathered in a way that respects the people behind it. Testing can also cause harm, especially when evaluation turns into surveillance or risky staging. The method used to validate the system should not create the very problem the system claims to prevent. Deployment changes the ethical picture because the same tool can feel very different depending on who is exposed to it and who has power over the outcome. The setting matters as much as the algorithm. Support and maintenance decide whether people have any real recourse after something goes wrong. If drift, complaints, or new use cases are not handled well, the system becomes brittle in practice. User reach matters because harm is not limited to the person standing in front of the device. Records, decisions, and downstream actions can affect many more people than the interface suggests. That broader view catches a common pattern. The final prediction is rarely the only source of harm. Once the system connects to cameras, alerts, dashboards, or human rules, its effect can become much more invasive. A warehouse security system makes the trade-offs easy to see because the benefits and the risks sit right next to each other. It can improve safety, but it can also create fairness, privacy, and oversight problems very quickly. A system that flags suspicious movement or unauthorized entry sounds practical at first. The ethical questions appear as soon as we ask who is watched, who is judged, and who bears the cost of mistakes. False suspicion is not evenly distributed when routes, disability access needs, or shift duties differ across workers. Even a statistically acceptable model can become unfair if it repeatedly singles out one group for attention and discipline. Privacy and consent become central when the system depends on continuous video, badge traces, or location patterns. The moral question is whether that collection is proportionate, clearly explained, and limited to what the job truly requires. Testing can also create harm if workers are staged as suspects or observed in ways that feel like surveillance. That kind of evaluation may validate the product, but can also normalize a damaging relationship between management and staff. Support matters because people need a way to challenge mistakes. Without appeal, human review, or an accountable owner, the system turns routine operations into opaque judgment. Ethical review has to count both the immediate injury and the slower effects that spread through behavior and trust. A system can be wrong in obvious ways and still cause broader damage, even when no single alert looks severe on its own. Direct harm includes things like wrongful suspicion, embarrassment, intrusive monitoring, or biased treatment. Indirect harm is quieter. People may stop reporting problems, trust may fall, and employees may feel watched even when they're doing nothing wrong. Indirect effects can also reach beyond the workplace itself. A security system may replace human roles or demand heavy infrastructure. So the ethical review has to look at the surrounding system, not just the software. A broader review group sees more than a narrow product team usually can. Different roles notice different failure modes, and that helps surface blind spots before they harden into policy. For a warehouse system, the review should include people who understand operations, privacy, safety, legal constraints, and the worker experience. Each of them may spot a risk that the others would miss. That participation is not bureaucracy for its own sake. It helps the team decide whether a harm is accidental and fixable or structural and hard to justify, and it forces early clarity about misuse, alerts, disablement, and correction. This becomes a real professional skill for employers and technical teams. The job is to identify ethical risk early, document it clearly, and explain whether the project should proceed, be revised, or stop. The practical rule is to surface concerns early enough to do something about them. Moral review is useful only when it leads to a concrete decision, not when it sits in a report and disappears. When a concern can be reduced through design changes, narrower data use, stronger oversight, or better consent, the project should be revised and documented. If the harm cannot be reduced to an acceptable level, the correct decision is to stop. A green light at launch is not the end of the process. Usage changes, data shifts, model drift, and new combinations with other tools can all turn a once plausible system into an unacceptable one. That means ethics has to become part of maintenance. The team needs to keep the risk list alive, revisit assumptions, and challenge the system again whenever the context changes. That discipline protects people and also clarifies what the project is allowed to be. It gives leaders and teams a decision they can defend to colleagues, to users, and to the public. Business feasibility asks whether a technical idea is worth doing for the organization, not just whether it can be built. The main test is value under real constraints. That blunt question keeps a project grounded. If the answer is unclear, the work may be interesting but not justified. A project can be clever, elegant, and fun to prototype, yet still fail the business test. Feasibility means checking both the value it creates and the ability to support it over time. Novelty only tells you that an idea is new or technically impressive. Value depends on whether someone in the organization gains something concrete from it. Different people care about different outcomes: speed, cost, coverage, workload, or fewer errors. If you cannot point to a specific beneficiary and a specific benefit, the project is still just an idea. Stakeholders need one shared definition of success, or evaluation turns into argument. The outcome, the target improvement, and the conditions for calling it a win all need to be concrete before results appear. The real question is whether the proposed AI approach beats what already exists. If the current process is already accurate, fast enough, and affordable, the business case may be weak even when the model itself looks strong. A warehouse setting makes the trade-off easier to judge because the value is tied to a clear operational goal: faster intrusion response. That gives us a concrete place to test the idea. Imagine an edge detector that spots unusual movement and alerts guards sooner. Riverwatch Node can stay in the background, but Freshline Inspector gives a more concrete deployment example for weighing value and practicality. A low-cost mock notification system can test the workflow before full development. A person or a script can trigger the alerts behind the scenes, so the team can experience the process without paying for the full build. That kind of mock-up can reveal whether the alerts help, confuse, or interrupt the guards. If the experience feels useful, the case for further work gets stronger. If it feels awkward, the warning sign appears early. The baseline is the existing guard process, camera watch routine, or radio escalation path. That is the real competitor, so the AI version has to outperform it in a meaningful way. If the current workflow already responds fast enough, the new system may add complexity without adding value. Strong ideas still have to beat the process already in place. Stakeholders should agree on the target improvement first, such as a faster response time or a larger share of incidents handled within a window. That way, the evaluation has a fair standard instead of a moving target. Measure the mock system against both the threshold and the current workflow. If the existing process already does the job, choosing not to build AI at all can be the best business decision. A project can be useful and still fail if no one can sustain it. Feasibility includes the practical burden of keeping the system running after launch. Support depends on whether the organization has the people, time, money, and maintenance capacity to carry the work forward. A prototype is not enough if the team cannot operate and update the system later. A warehouse deployment may need rugged devices, process integration, and someone ready to handle failures or unexpected behavior. Those responsibilities are part of the business case, not an afterthought. A feasibility check has to allow a negative answer. If the value is weak or the support burden is too high, stopping early can be the right outcome. A mock test may confirm the idea, narrow the problem, or show that the project should end. Real go/no-go decisions depend on value, baseline performance, and whether the organization can sustain the work. That judgment is a core professional skill in applied AI. Employers need people who can weigh business goals, operations, and trade-offs, not only people who can train models. The best projects are the ones that create defensible value inside the limits of the organization. A good demo matters, but lasting support matters more. Business feasibility asks whether an edge AI idea earns its place in a real organization. The focus here is on value, support, and cost, because a project only matters when it can survive all three. A good idea is not enough on its own. It becomes viable only when it creates measurable value, wins support from the people affected by it, and fits the organization's ability to build and maintain it. That means the benefit has to be named in practical terms. Lower losses, faster response, fewer interruptions, safer operations, or direct revenue all count. But the gain has to be specific enough to justify the work. The first test is whether the project solves a problem someone truly cares about. If the benefit is vague or hard to measure, the case for building it is still weak. Different groups look for different gains. An operator may want fewer false alarms. A customer may want faster service, and the organization may care about avoided losses or lower labor pressure. Many ideas fail because the payoff is too diffuse to justify the effort. A technically interesting system can still be a weak business choice if the benefit is not large, visible, and convincing to the people who would sponsor it. Upside alone does not make a project feasible. The cost side matters too, because budget, expertise, timeline, integration, and support all shape whether the idea can really survive. A business case has to include the full cost of ownership. That means looking beyond the prototype and counting the work needed to deploy, connect, and keep the system running. A team may build something that works in the lab and still struggle in the field. Real feasibility asks whether the model can be updated, whether failures can be handled, and whether the system stays usable after the early excitement fades. That matters especially at the edge, where the product includes hardware, software, workflow changes, and human responsibility. The organization has to carry the whole system forward, not only the algorithm. A warehouse security example makes the trade-offs easier to see. The idea sounds useful, but the real question is whether the benefit is strong enough to justify the effort and expense. The proposed system shifts guards away from constant monitoring and toward responding to alerts. That could reduce theft, damage, and unnecessary patrols, so the appeal is easy to understand. That is the sharper business question. A helpful result still has to earn its keep against the money, effort, and disruption required to build it. A Wizard of Oz prototype can test that idea at low cost. The system feels automated to the user, but the response is produced behind the scenes, which lets the team learn whether guards trust it, use it, and respond faster with it. The test has to be designed around clear success measures. Shorter response times, fewer missed incidents, and lower guard workload all make sense, and the AI version still has to beat the current non-AI process. That comparison is essential because feasibility is always relative. The real question is whether AI is the best choice, not whether it is possible to build one. A project can be technically possible and still be the wrong investment. Business feasibility asks whether this approach is better than the current one, not just more advanced. Sometimes the existing process is already reliable and cheap, so AI only adds complexity. In that case, a better staffing pattern, a cleaner workflow, or a rule-based alert system may deliver the outcome with less burden. That is responsible decision-making, not resistance to AI. The project should earn approval by improving the situation enough to justify its own costs and effort. Support matters as much as the business case on paper. If the people affected by the system do not trust it or want it, the project can stall no matter how good the idea looks. Those roles have to be identified early. The team needs to know who owns the problem, who uses the system every day, who approves the budget, and who will maintain it after deployment. In the warehouse, each group sees the system differently. Guards may worry about extra work, managers want evidence of better response, and maintenance staff want a clear plan for updates and failures. A mature feasibility review does not always end with approval. Sometimes the right answer is to revise the idea, and sometimes the right answer is to stop. When a value is too small, support is too weak, or a cheaper alternative is already good enough, not building the AI system is the correct choice. That decision can feel disappointing, but it saves time and avoids unnecessary complexity. Walking away early leaves the team free to focus on problems where edge AI has a real advantage. Business feasibility should act like a gate, not a formality. If a project cannot show value, win support, and beat the current alternative on cost and practicality, it should not move forward. The discipline is straightforward, but it is demanding. Show that the system is worth more than what it replaces. And if that proof is missing, the strongest move is often to walk away. Dataset feasibility decides whether an edge AI idea has a real path to data before any deeper design work begins. The point is to catch data problems early, while the project is still easy to revise. Feasibility belongs at the front of the decision process, because a project can fail even when the business need is clear. If the data cannot support training and testing, the rest of the plan does not matter yet. That order matters. Architecture and model ideas are easy to discuss, but none of them can succeed if the data supply is weak, inaccessible, or too expensive to gather. The question has two parts: how much data the task likely needs, and whether that data can actually be collected, accessed, labeled, and kept current. A project only looks feasible when both parts seem realistic. The first step is a rough estimate, not a final count. After that, the real test is whether there is a believable way to reach that amount of data in the target setting. Good estimates come from comparable tasks, not from guessing in the abstract. Benchmarks and published datasets give a starting point for what a plausible data scale looks like. A precedent can show that a task has been solved before and that a model-based approach is reasonable. It does not prove the same result will hold in a different environment with different constraints. Acquisition is the harder half of the check. Access, sensors, permissions, rare cases, cost, privacy, and timing all decide whether the data can really be gathered in practice. A concrete use case makes the check easier to judge. A warehouse security task gives us a setting where precedent, environment, and collection limits all have to be weighed together. A related benchmark can tell you whether people detection has enough data behind it to be trainable and testable. That does not solve the warehouse problem, but it does show whether the core task has a data-backed foundation. That kind of precedent is encouraging because it reduces uncertainty. It can guide your first estimate for label needs, class structure, and a baseline approach. Local conditions can change everything. Poor lighting, awkward camera angles, uniforms, equipment, clutter, and occlusion can make a real site much harder than public data suggests. That mismatch is the warning sign. Public data is most useful when it informs the estimate, not when it is treated as proof that the deployment site will behave the same way. Weak signals need a hard decision, not wishful thinking. If the data path looks too fragile, the project should be narrowed, changed, or stopped before more effort is spent. When data is sparse or mismatched, optimism is not a strategy. A responsible team may need a smaller scope, a different deployment context, a simpler rule-based method, or a completely different use case. Many projects fail only after the team discovers that examples are rare, labels are messy, or the environment keeps changing. By then, time and credibility have already been spent, so early caution matters. Judging feasibility quickly is a career skill because it protects both the project and the organization. The people who can identify weak data early are often the ones who save the most effort. Employers value people who can avoid doomed projects, not just people who can train models. Clear judgment about data saves money, prevents repeated false starts, and shows real technical maturity. A practical check has three parts. First, find a comparable task or data set. Second, judge whether the target setting is close enough to matter. Third, confirm that the missing data can still be collected or accessed without major risk. A good edge AI idea needs more than usefulness. It needs a believable path from concept to testable system, and that path starts with data that can actually be obtained. Data feasibility shapes whether an AI project can move from idea to deployment. The focus here is on how to judge whether the right data exists, whether it matches the real setting, and what that means for project decisions. Data is not a separate afterthought. It sits alongside business value, deployment limits, and technology fit. A model cannot be trained or trusted without representative data, and even rule-based systems still need data to test edge cases and confirm the rules behave sensibly in the real world. The first judgment is whether the task needs a lot of data or only a modest amount. The second is whether that data can actually be sourced, because a small task can still be infeasible if the right examples are private, rare, costly to label, or unsafe to capture. At this stage, a rough estimate is more useful than fake precision. Prior papers, benchmarks, products, and public datasets can narrow the uncertainty by showing whether similar problems have been solved and what scale of data they seem to require. A public dataset can tell you that a problem class is real and that labeled examples exist, but does not guarantee success in your own environment. The gap between a benchmark and the deployment site is where feasibility often changes. For a warehouse person detection system, a public dataset is a useful first signal. It shows the task is tractable in general and gives a starting point for model development, even if the benchmark conditions are only an approximation of the real site. The real environment may be darker, busier, angled differently, or full of glare and occlusion. Those differences matter because models learn from the data they see, not from the abstract idea of the task. A strong benchmark score can still hide a deployment problem if the target domain is far from the source data. Lighting, camera position, seasonal change, and operating conditions can push the model outside the range where the training data was informative. Weak data evidence should trigger a decision, not a delay. If the needed data is inaccessible, too noisy, or too unlike the target setting, the problem may need redesign. The sensing setup may need to change, or the project may need to stop. That can feel harsh when the business case is attractive, but early revision is far cheaper than months of work on a model that cannot generalize. Many failures blamed on algorithms actually come from data that was never right for the deployment task. The real mistake is usually upstream. The team optimized for the data that happened to be available instead of the environment the product had to serve. Once that happens, even good modeling work can fail for reasons no optimizer can fix. A simple early workflow keeps the evaluation honest and practical. It forces attention on the deployment setting first, then on whether the available data can actually support that setting. Start by defining the setting in concrete terms. The more specific the environment is, the easier it becomes to judge whether any dataset is a real match or only a rough approximation. Then estimate the amount and variety of data. Look for public, internal, or partner sources and compare those sources to the target environment rather than to the abstract task. That comparison leads to a clear decision: proceed, revise, or stop. This process saves time and money, but it also shows a kind of leadership that matters in practice. Teams value people who can tell when a project has no viable data path instead of pushing ahead on optimism alone. The decision point is narrow but important. Do not ask only whether the problem is interesting. Ask whether enough relevant data is likely to exist for the exact environment you want to serve, and treat precedent as an opening rather than a verdict. Technological feasibility asks whether an idea can survive real constraints and become a workable system. The focus here is on translating a use case into technical options and judging whether any of them can actually be built, deployed, and maintained. At this stage, the idea is no longer judged as a wish. It becomes a design problem, where the question is whether the concept still holds up once the real-world limits are applied. The useful habit is to trace the whole chain from need to implementation. You ask what the system must sense, what data it produces, how that data is prepared, how much compute is needed, and where the work should run, because all of those pieces have to fit together. The first pass should focus on the components of the system, not on a fashionable algorithm. Sense, infer, and deployment environment are the starting questions because they determine which kinds of solutions even belong in the conversation. A camera, a vibration sensor, and a thermal sensor lead to very different technical paths. Once the data type changes, the likely methods change too, so the model choice comes after the sensing and representation questions. The same operational need can be framed in different ways, and each framing changes the solution space. A security task might become detection, identification, or anomaly spotting, and each of those points toward different techniques and different levels of complexity. A feasibility review should compare options, not settle on the first idea that sounds clever. The point is to line up multiple approaches so the trade-offs become visible. A sensible comparison includes the existing baseline as well as technical alternatives. If the current method already handles the job better on cost, latency, or reliability, a new system has to justify why it deserves to replace it. Cloud systems offer central compute and easier management, but they depend on network quality and can add transmission costs and delay. Edge and on-device options reduce bandwidth pressure and latency, yet they force the model to fit tighter limits on power, memory, and heat. Combining several sensors can make the system more resilient because one signal can back up another. The cost is extra coordination, synchronization work, and more operational complexity, so the best design is the one that survives the constraints without becoming unmanageable. Complex applications are easier to judge when they are split into pieces. Each piece can then be matched to the right technique instead of forcing one model to do everything. One part of the system may be object detection, another may be a simple rule, and another may be anomaly detection. Once the task is decomposed, the architecture usually becomes much clearer because each chunk asks for a different kind of tool. Hardware limits can make a design impossible even when the idea looks clean on paper. A small device may handle a compact model, but fail under the load of a large detector, and in brownfield settings the installed equipment often sets the boundary before the project even starts. Feasibility tightens quickly once real constraints are included. Cost, staffing, maintenance, and existing infrastructure often decide whether a design survives or gets dropped. These practical limits are not side notes. They are part of the technical judgment. A system can be correct in principle and still be a bad choice if the organization cannot support the staffing, cooling, space, or procurement cycle it requires. Human workflow belongs in the same review because the system has to be usable by real operators. If alerts are confusing or too frequent, the design may technically function while still failing the people who depend on it. A constrained deployment makes the logic of feasibility easier to see. Limited power and unstable connectivity force the system toward a smaller, leaner design. A field node with tight energy and network limits cannot afford excess complexity. That kind of environment shows how constraints do more than restrict ambition. They shape the form of the solution itself. The real question is broader than model availability. It is about whether an entire system can be built and run responsibly in the target environment. A model by itself is not the finish line. The test is whether the full solution can be integrated, operated, and maintained in a way that still fits the environment and the task. That judgment is valuable because it prevents wasted prototypes and unrealistic commitments. A strong engineer can narrow a vague requirement into a few defensible options and recognize when a deployment cannot survive the available data path, hardware, or field conditions. The practical sequence is to translate the idea into technical forms, compare them against the baseline, split the problem, and apply constraints early. If one path survives, the project is plausible. If none do, the responsible move is to revise the problem or stop. Technological feasibility becomes useful when it moves from abstract possibility to concrete design choices. The goal here is to compare real solution shapes and see which ones can actually survive the constraints of a warehouse, a team, and the available hardware. A good feasibility check starts with one candidate problem and several possible ways to solve it. That comparison tells you far more than a yes or no question about whether AI can do the task. Because the real issue is whether a solution fits the environment, the budget, and the operational needs. The first move is to break the goal into the ingredients a system would actually need. That means identifying the sensors, the data rate, the timing constraints, and the exact kind of task the system is being asked to perform. A warehouse security goal can be framed in different ways, and each framing changes the design. Detecting intrusions, flagging suspicious motion after hours, and identifying personnel all sound related, but they lead to different inputs, different models, and different levels of operational burden. That is why feasibility is a comparison exercise rather than a single-shot decision. Before settling on one architecture, it helps to list a few plausible directions and see how each one handles the same problem under different constraints. A staff baseline gives a real-world reference point. If people already catch most incidents quickly enough, then automation only needs to justify itself against that existing performance, not against an idealized target. A cloud pipeline can make sense when centralized control and heavier models matter more than local speed. The trade-off is that every video stream now depends on network quality, upload cost, latency, and privacy controls. An edge server sits closer to the site and can process streams locally. That often gives a useful balance. Faster response, less bandwidth use, and still enough compute to run more capable models than a tiny device could handle. On-device inference pushes the work all the way to the camera or microcontroller. It improves resilience and reduces network dependence, but also forces a hard check on memory, power, thermal limits, and model size. Sensor fusion changes the problem itself by combining multiple signals. Video, motion sensors, and access control events can support one another, which may improve reliability, but it also adds integration work and more places for the system to disagree or fail. These options are not just different ways to package the same solution. Each one changes the requirements, so the architecture choice and the technical problem are tied together from the start. Two useful reference points are the non-AI baseline and the cloud design. Looking at both helps separate what the system truly needs from what only seems attractive at first glance. A baseline keeps the comparison honest. If trained staff already handle most incidents well enough, then the question becomes whether AI closes a real operational gap, not whether it merely sounds more modern. Cloud systems are attractive when centralized management and larger models matter. The price is dependence on connectivity, extra bandwidth use, slower reaction time, and stricter governance when data leaves the site. Once the baseline and cloud trade-offs are clear, the question shifts to how far the computation should move toward the device. That is where edge servers, on-device systems, and sensor fusion become the main design candidates. An edge server is often the middle ground. It keeps inference close to the warehouse, which improves responsiveness and reduces network traffic while still allowing stronger compute than a fully embedded device. On-device designs are even more local, and that can make them robust when the network is unstable. The limiting factor is the device itself, because some models will simply not fit the available memory, power, or thermal budget. Sensor fusion does more than shrink deployment size. It reshapes the system around multiple signals. When the signals reinforce each other, false alarms can drop, but the engineering effort rises because calibration, coordination, and conflict handling all become part of the job. A single business request often hides several different technical tasks. Breaking it apart first makes it much easier to choose the right model, the right rule set, and the right evaluation criteria for each piece. Detecting intrusions may involve first finding people or vehicles, then deciding whether their behavior is unusual for that place and time. Identifying workers may be better handled with embeddings and comparison against a database than with a brand new classifier for every face. Some subproblems belong to explicit logic instead of learning. Door open events, shift schedules, and fixed access rules are often clearer when handled as rules, while detection and anomaly scoring can use learned models where variation matters. After the problem is decomposed, the real-world limits start trimming the list of options. Cost, expertise, hardware, and supply chain reliability decide which ideas remain viable. A strong feasibility review checks whether the environment can support the design. Existing cameras, older devices, limited staff expertise, or hard-to-source chips can all rule out an architecture before it ever reaches production. Constraints do not just slow a project down. They can force the whole workflow to change. If a design creates alert fatigue, fragile handoffs, or training demands the team cannot meet, it may be infeasible even if the underlying model works. Employers value judgment that can reject a poor fit before time is wasted. A cloud design may be too bandwidth heavy. An edge server may be the better compromise. On-device inference may be unrealistic, or sensor fusion may be too hard to maintain. By the end of feasibility work, the goal is to have a small set of credible options and a clear reason for each one. If none of them fit the environment, the honest move is to revise the problem or stop before investing in a design that cannot succeed. Feasibility review ends with a choice: proceed, revise the problem, or stop. That decision matters because the analysis is meant to guide action, not leave the project suspended in uncertainty. Once the review is complete, the question changes from possibility to judgment. The team has enough evidence to decide whether the idea should move forward, be reshaped, or be put aside. When the solution ideas do not fit the real limits, forcing them usually wastes effort. A better move is to narrow the task, change the scope, or adjust the success condition until the problem matches what is actually possible. That back and forth is normal in Edge AI. A project can become workable after a better framing choice, or it can become less attractive once deployment, maintenance, and human impact are examined more closely. A review should produce a clear outcome and a clear reason. If the project is revised, the team should name what changed and test the new version against the same feasibility checks. If it stops, the reasons should be documented so the block paths are still useful knowledge. Not every blockage has the same meaning. Some constraints come from current hardware or tools and may improve later, while others point to real harm, misuse risk, or unsafe deployment that should not be ignored. A concrete project often reveals the decision gate very quickly. If the value is real but the data, camera placement, or privacy risk is not acceptable, the right response is to narrow the task to a safer subproblem or hold it until the missing pieces are addressed. That kind of judgment matters beyond the project itself. Employers value people who can explain what should be built, what should wait, and what should be abandoned because they save time, money, and trust. Once the feasibility question is settled, the work shifts from analysis to action. The next step depends on whether the project is ready to move into planning or needs another pass through reframing. A feasible project should not stay in analysis mode. At that point, the team starts defining stakeholders, tightening success metrics, setting constraints, and deciding what the first prototype must prove. A simple compare and decide table helps separate promising ideas from risky ones and from dead ends. It gives a quick way to judge whether the next move is proceed, revise, or stop. When the project does not pass, the responsible response is just as clear. A clean stop can be the best result when the constraints are too strong or the risks are not acceptable. Feasibility review is where a project earns a proceed, gets reshaped, or gets stopped. The point here is to turn all the earlier checks into a clear decision instead of leaving the team stuck in evaluation. A feasibility review should not sit on the side as a formality. After ethics, business value, dataset readiness, and technical constraints have been checked, it has to produce an actual choice the team can act on. Proceed means the problem definition and solution path are strong enough to justify investment. The team does not need certainty at this stage. It needs a defensible reason to keep going and build a first prototype. That usually means the major risks are understood, the limits are manageable, and there is a believable path to something useful. The project is not finished, but it has passed the point where further work makes sense. Revision is the right move when the need is real, but the current framing is off. The issue is not the goal itself. It is that the question needs to be changed so the solution has a fair chance of working. A project can be too broad, too vague, or blocked by a constraint that only became visible after review. Rather than forcing the original answer, the better move is to reshape the problem around the facts now on the table. That might mean narrowing scope, choosing a different environment, or reducing the performance target. After that, the team should brainstorm again under the new limits and run the feasibility checks one more time. That loop is part of the method. Stop means the project should not move ahead in its current form, and sometimes not at all. A no-go decision can be the most responsible outcome when the evidence says the risk or cost is not acceptable. Stopping prevents wasted effort and avoids building something unsafe or misleading. It also keeps the organization from chasing an idea just because it sounded attractive at the start. Some obstacles are not temporary. If the data cannot support the task, the hardware cannot meet latency or power limits, or the ethical risk is too high, the correct decision may be to walk away. When real-world constraints break the first solution, the work should not stall. It should move through a disciplined cycle that tests whether the problem needs to be reframed before anything else is built. The sequence matters. Identify the blocking constraint, revise the problem, generate fresh ideas, and check feasibility again. That keeps the team from treating the first solution idea as if it were already the correct one. Many projects fail because the team gets attached to the first framing. The goal is not to force an edge model at all costs. It is to find a most defensible outcome, whether that is edge AI, a simpler rule-based system, a cloud workflow, or no system yet. Riverwatch node makes the pattern concrete. A broad goal like detecting every concerning event across a wide river corridor may sound impressive, but once the constraints are examined, the scene is too variable and the data are too sparse for confident generalization, so the team has to narrow the task or defer it. Technical elegance and practical viability are not the same thing. A system can look impressive on paper and still fail the review of privacy, environment, or hardware limits make deployment irresponsible or unreliable. A warehouse security system, for example, may promise continuous video analysis and local inference, but the privacy risk or the hardware budget may make it a bad fit. A compelling model does not override a bad deployment context. That distinction matters a lot in edge AI. Feasibility asks not only whether the system can be built, but whether it should be built in that form, for that setting, under those constraints. When the answer is reject or defer, the decision needs a record. The point is to capture the reasoning so the organization remembers what blocked the project and why the call was made. Good documentation should name the constraint, the assumptions that failed, the options that were considered, and the reason for the final choice. That turns the decision into organizational memory instead of a forgotten dead end. A rejected project can define the boundary of what the organization can support right now. A deferred one can show what data, governance, or infrastructure would need to improve before the idea becomes realistic. Discipline go or no-go judgment is a real product and engineering skill. Teams value people who spot constraints early and explain a decision clearly in business, ethical, data, or technical terms. The person who can say a project is interesting but not feasible, yet saves time and reduces risk. That judgment is as valuable as moving quickly because it keeps effort pointed at problems worth solving. A feasible decision should turn directly into planning. Once the project has passed review, the work shifts from evaluation into concrete setup and execution. That means naming stakeholders, agreeing on success criteria, identifying resource limits, and outlining the first prototype. Feasibility is the gate. Planning is what makes the project real. The habit to keep is simple. Do not push past a failed feasibility test. Revise the problem, test the solution space again, or stop with a well-supported rationale. If the answer is yes, move straight into planning. And if it is no, treat that answer as useful information. Edge AI succeeds when the project is planned around constraints, not around a model choice. The main idea here is to define success, test limits early, and avoid building something technically clever that cannot survive real use. The first decision is the problem definition, because that shapes every technical choice that follows. A good model only matters after the team knows what outcome it must produce and what it has to fit inside. A small device does not make the project small. It makes the constraints more visible. Before hardware or architecture enters the discussion, the team needs a clear target and a clear sense of the limits the system must respect. That is why edge work usually has to move in short learning cycles. Early assumptions are often wrong about data quality, latency, hardware fit, or user acceptance. So the safer approach is to test the system, learn from the result, and revise the design. Performance only becomes useful when real people can judge it against their work. The goal is to turn abstract model metrics into outcomes that operators, safety staff, and product owners can agree on. The right thresholds come from the people who will depend on the system, not from the engineering team alone. They care about whether the result is usable, safe, and tolerable in daily work. So those voices need to shape the target from start. Those questions turn a vague goal into measurable limits. Once the team can name how many errors are acceptable, how much delay is tolerable, and how much human review is still workable, the project has a real operating target. Freshline Inspector shows the value of beginning with an ordinary end-to-end pipeline instead of waiting for the perfect device. That keeps the team focused on what actually works in practice, while stakeholders decide what counts as good enough before custom hardware enters the picture. Ethics is not a final check after the technical work is done. It belongs in the success criteria because a system that is unsafe, unfair, or impossible to oversee has not really succeeded at all. A high accuracy score does not excuse harmful behavior. If the system creates avoidable risk, bias, surveillance concerns, or weak accountability, then the design still needs work even if the model looks strong on paper. Edge systems often run in physical spaces where the impact reaches people who never opted in. That makes privacy, transparency, and error recovery part of the plan from day one, because those problems are much harder to fix after commitment. A credible plan has to survive practical limits as well as technical ones. Time, budget, team skills, and device availability can each determine whether the project reaches deployment or stalls halfway through. The model is just one part of the schedule. Edge projects also depend on integration work, maintenance, sensors, deployment, and the surrounding workflow, so the plan has to account for all of that effort. Time is often lost on model tuning while integration is delayed. Budget goes beyond software because devices and testing cost money. Expertise may be spread across embedded systems, networking, and operations, and the intended hardware may simply not be available or capable enough when the team needs it. When those limits are treated as design inputs, the team can make honest choices early. If the costs, skills, and hardware headroom are still unclear, the plan is not ready yet. The quickest way to expose system risk is to connect the whole chain early. A small prototype can reveal whether the pieces work together before anyone invests too much in the wrong direction. The prototype should include the full loop, not just the model. Once data capture, inference, messaging, decision logic, and user interaction are linked together, the team can see how the system actually behaves as a system. A model that looks excellent in isolation can still break under real camera placement, network delay, or user expectations. End-to-end testing catches those failures early, while changes are still cheap. Polishing the model too early can hide bigger problems in the pipeline. If the camera, placement, alert design, or workflow is wrong, a slightly better model will not fix the project. So the team should learn that before the schedule hardens. Hardware choices need to start early enough to reveal hidden limits. The aim is not to freeze the final product immediately, but to make sure the workload, peripherals, and environment can all be supported. If hardware is left too late, the team may discover that the target device cannot handle the compute load, the sensors, or the enclosure constraints. Early checks prevent that kind of redesign shock. Development boards are useful because they let the team test the whole setup before buying production parts. That is the stage for checking whether the sensor chain works, whether latency is acceptable, and whether the system needs more compute than expected. Freshline Inspector follows that safer path. Prove the inspection pipeline on development hardware first, then specialize later. Doing it this way also reduces supply chain risk, because a scarce part is much less dangerous before the design is frozen. The first platform should have breathing room. A design that only barely works in the lab often becomes fragile once heat, power variation, and field conditions start to matter. Complexity is only worth paying for when it changes the outcome. If a simpler workflow or a less specialized device meets the target under the real limits, then simplicity is the better engineering choice. A more modest solution can be the right one when it already satisfies the need. Extra complexity often adds cost, risk, and maintenance burden without improving the result. Good planning protects the organization from wasted effort. The valuable engineer is the one who can define success clearly, spot risk early, and choose the version that fits the real limits instead of chasing the most ambitious design. The practical habit is to make the first plan small, honest, and testable. Confirm the stakeholders, write down the constraints, start on low-risk hardware, build the first end-to-end prototype, and let that prototype decide whether the idea should go forward, be revised, or be stopped. Edge AI planning turns a promising idea into a workable system by tying together performance, constraints, and real-world deployment. The goal here is to see how that planning keeps the project grounded instead of drifting into guesswork. A good idea only becomes useful when it can survive contact with limits. The plan is what separates a serious project from an optimistic claim. Once the idea passes a basic feasibility check, the real work starts. Planning gives the team a structure for decisions, so the project does not wander into expensive uncertainty. Edge AI touches several areas at once, and each one can pull the project in a different direction. Planning forces those trade-offs into the open early, before teams lock themselves into conflicting assumptions. A small example makes the idea concrete. Riverwatch Node is a monitoring system whose first job is not to be fancy, but to show that the device can sense the right event, make the right decision, and send an alert people trust. Performance needs measurable boundaries, not vague hopes. The next step is to decide what counts as success and what kinds of mistakes the system can tolerate. The team needs shared targets for detection quality, speed, and error rate before anything is built. Those targets should come from the people who will live with the system, because different users make different trade-offs between false alarms and missed events. Ethical review belongs in the performance discussion, not after deployment. If the system affects people, animals, or property, the team has to think about harm, unnecessary data collection, and when a human should stay in the loop. That trade-off depends on a real use case. A flood of weak alerts can be worse than a cautious system, while in another setting a missed event carries the bigger cost, so the standards have to match the job. Constraints shape the design from the beginning, so the plan has to start there. Time, budget, expertise, and hardware limits decide what kind of system is realistic. Resource limits are not paperwork. They determine what can actually be built and supported. If a project assumes endless iteration, it often discovers too late that the team cannot maintain the model, the device, and the deployment process at the same time. A practical plan asks blunt questions about ownership, skills, and schedule. Those answers tell the team whether it should experiment broadly or commit early to a narrower path. A modest system that can be delivered and improved is usually the smarter choice. For Riverwatch Node, that may mean limiting sensors, simplifying the alert path, and keeping the first version focused on something the team can actually support. The safest early prototype is one that connects the full chain, even if it is rough. That exposes problems that isolated model work can hide. Component-level success can be misleading. A model may work on its own, but fail under real camera input, network delay, battery limits, or alerting logic, so the full workflow has to be tested together. A crude prototype is often more useful than a polished piece of code. Even a manually assisted setup can reveal whether people understand the alert, trust the response, and act the way the system expects. Each prototype loop should check the whole chain, not just one part of it. That way the team can spot hardware limits, user mismatch, or data problems before they become expensive to fix. Hardware is part of the first design decision because the device sets real limits on memory, compute, heat, and power. The plan has to account for that from the start. The team should decide what kind of device it needs and what board can support early testing. Extra headroom matters because early estimates are often too optimistic, and it is hard to repair a hardware mismatch after the rest of the system is built around it. Many teams begin with more capacity than the final product needs, so they can learn without hitting a wall immediately. Once the workload is understood, the system can be trimmed down to something more efficient. For Riverwatch Node, the first hardware choice should support experimentation, logging, and integration work. The better question is whether the device helps the team validate the system without trapping it in a fragile design. Employers value the ability to shape a system, not just build isolated pieces of it. The strongest candidates can connect technical choices to real constraints and real outcomes. A strong edge AI engineer can set success criteria, estimate limits honestly, and keep a project from spending time on the wrong solution. That broader judgment is what makes the technical work useful in practice. That kind of thinking helps a team avoid costly false starts. It shows that the person understands prioritization, not just implementation. A project becomes actionable when the next decision is visible. The team needs to know what success looks like, what limits apply, and what happens if the idea does not hold up. When the plan is clear, the team can move forward with confidence. When constraints reveal a weakness, the right move is to revise the problem or stop before more time is wasted. Riverwatch Node follows that path. Begin with a small end-to-end prototype. Measure it against concrete standards, improve within the real limits, and add complexity only after the workflow proves itself.